Okay, we are on 2.1, measuring the rate of chemical reactions. We're going to take a look at the warm-up where we're calculating the average velocity, which is known as rate of a car over the entire time period. We have data, distance traveled in kilometers per time in minutes. They want us to calculate the average rate or the average velocity in kilometers per minute. So since I initially start out at 0, 0, I'm going to use these points here, the 125 and the 100. You're going to take 125 kilometers divided by 100 minutes. You're going to end up with 1.25 kilometers per minute. If you want kilometers per hour, you're going to have to convert minutes to hours. So if you write that as a fraction, 1.25 kilometers over 1 minute, and then there are 60 minutes in an hour. You're going to end up with 75 kilometers per hour. Why do we refer to this as an average rate? Well, the rate is not consistent if you look at the data. It changes over time. So that's why the rate isn't consistent. It changes, so we're using the average rate by looking at these last values here compared with the initial values here. A unit of blank is always placed in the denominator when calculating rate. Well, we have time in the denominator, okay? Now, when we're measuring the rate of a chemical reaction, we're converting reactants with a unique set of properties to products with a completely different set of properties. So we're going to look at chemical kinetics, which is where we investigate the rate at which these reactions occur and what factors are affecting them. If you're looking at the explosion of a firecracker, that takes less than a second, whereas metabolizing something that you eat can take several hours, or rusting of a bicycle can take weeks to months to occur. So reaction rates are determined by you observing something like the disappearance of a reactant. Maybe you're losing a gaseous reactant or a solid reactant or a pH from an acidic reactant, or the appearance of a product. Maybe you're producing a gas. You're going to look at the volume of gas produced. Or maybe you're producing a base. You're going to look at the difference in pH. There has to be some sort of a measurable property associated with the change in the quantity of reactant or product that you can use to determine the reaction rate. So that means you have to look at a balanced equation, look at states of matter, and think about things that you've learned from last semester. And you also have to think about, what do I have in the lab to measure? What can I use? And then you'll also be looking at the units that are associated with making that measurement. So in order for these questions to be answered and you determine the rate, you can use this equation where the average reaction rate is the change in a measurable quantity of some chemical species, whether it's a reactant or product, over time. For most reactions, the rate is going to be the greatest at the beginning of a reaction, and it'll decrease over time because as the reaction happens, you're going to be consuming reactant. So the forward rate, which is converting reactants to products, you might think of it as having a negative value, but when you calculate it, you're actually going to be representing the absolute or positive value of that rate. So let's take a look at the quick check here. We have the decomposition of thionyl chloride, and they remove small samples. These small samples are known as aliquots, and we do this during a titration, and we can calculate the concentration that's present over time as we remove small aliquots. And they've given you a data table here. You've got the concentration of thionyl chloride versus time, and you want to plot that on this graph. What I recommend you do is do increments of 10 here. Go from 0.1 to 0.2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This would be 0.1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This would be 0.2. And then since your x-axis is going up to 600, I would recommend doing these in fours. So this would be 100, this would be 200, this is 300, 400, 500, and 600 seconds. And then you're going to plot these. So at 0.2, you're up here. And then at 100.16, you're here, and then 200.127 is here, 300.1 is here, 400.08 is here, and then 500.06, 7 is there, and then 600.06. 1, 2, 3, 4, 5, 6. Okay, so you look something like this. And then if you turn the page to the questions, it says, what would the slope of this graph, the change in concentration of thionyl chloride versus time, represent? Well, this is going to be the rate of decomposition of thionyl chloride, okay? And then number 2, it says, how does the slope of the graph change as time passes? Well, doesn't it become less and less steep? Number 3, what does this indicate about the reaction rate? Well, the rate is decreasing with time. And number 4, what is the average rate of decomposition of thionyl chloride? Well, so what I would recommend doing is you're going to be using this last point and this initial point to calculate that. That's going to be the slope. So 0.06 minus 0.2, the unit is molarity, divided by 600 minus 0, that unit is seconds. You're going to end up with negative 2.3 times 10 to the negative 4th molarity per second, but we don't want to have that negative. We want the absolute value. This would be 2.3 times 10 to the negative 4th meters per second. Question number 5. How does the rate of 500 seconds compare to the rate of at 300 seconds? Well, here I'm at 500, and then here I'm at 300. And the rate at 300 definitely appears to be greater than the rate at 500. Number 6, suggest a way to determine the rate at the particular times mentioned in question 5. The rates at those particular instants are called instantaneous rates. So what you're going to do is you draw a line. If this is my curve here, you draw a tangent line that touches only that point. So you make it so that it would go something like this, and then you pick 2 points on that line, and you would calculate the slope to get the instantaneous rate of the reaction. Okay, so for number 6, you would find the slope of the tangent line drawn to the curve at that time. Okay, and then you would do the same thing at 500. You would have a tangent line that touches only at that point where the 500 seconds is. When you get to question number 7, they want you to actually calculate the instantaneous rate. So I picked 2 points on my 500 second line, and I calculated the change in y over the change in x. And I got 0.05 minus 0.08 divided by 575 minus 375. That was negative 1.5 times 10 to the negative 4th molarity per second. I want the absolute, so it would be 1.5 times 10 to the negative 4th molarity per second. Now, when I did it for 300 seconds, I ended up getting 2.1 times 10 to the negative 4th. Now, depending upon where you drew your tangent line and how you plotted things, what points you picked, you're probably not going to get exactly what I got. Yours will be slightly different. Let's go on to the next page. Let's talk about how we're going to measure things so that we can get the reaction rate. This is a very important section. So here what you want to do is You have to consider what we can change, like what quantity of reactant or product is actually going to vary, and what apparatus do I have available. The first thing you could look at is there a concentration of reactant in solution? That could be determined. Remember, concentration is referring to molarity, and this has to be dissolved in water. And in order to do something like that, what you could do is a titration of an aliquot, a small quantity of the reacting species that you draw out over time. Titration is also known as titrimetry. And the units here would be molarity over time, probably molarity per minute. If you have a gas that is being formed or consumed in a closed system, then you would use a manometer to measure the change in pressure. Okay, your manometer is over here. And if you're going to be using a manometer, you're probably going to be looking at units of kilopascals, which is a pressure unit, over time, probably per minute. Okay? What if you are looking at a gas that is produced in more of, you're producing a gas over water, you would be looking at gas volume using a eudiometer, which is down here, okay? The gas would be collected here above the water. So that means you're probably looking at units of volume over time, which would be something like milliliters per minute. If you have an open system and the gas is leaving, then you could just measure the mass change using a balance, which means you're probably looking at units of grams over time, maybe grams per minute if you're using a balance, okay? If you go on to the next page, if for some reason the amount of reactant or product can't be monitored directly, then you've got to think of some other way to monitor it. And one of those things that you could do is you could take a look at, if it's an aqueous solution, you could take a look at the solution's color. You could take a look at the solution's pH. If that's happening, then you could be using, for pH, you could be using a pH meter. And if for some reason you're going to be looking at color, then you could take a look at a spectrophotometer. Okay, so color kind of goes with spectrophotometer. They sometimes call them a colorimeter. But when you're looking at the color, this color and pH must be, the solution must be dissolved in water. And your units for the spectrophotometer are probably going to be in percent per minute or just per minute for those units. And then if you're looking at a pH meter, you may also be doing a titration, which means you're looking at molarity per minute, okay? And then if you're looking at an ion concentration, like you have an ionic compound dissolved, then there's going to be some sort of a charge that you can measure. That means conductivity. And the conductivity probes or conductivity meters are usually in per time, so something like per second would be what you're measuring that in, and that has to be dissolved in water as well. Okay. Now, if you take a look at the sample problem, you probably feel like I just threw a lot at you, but take a look at the sample problem. And they want you to think of different methods for measuring the rate of a reaction when an iron nail is put into concentrated hydrochloric acid. Well, iron is solid, and hydrochloric acid is dissolved in water, and it has a pH less than 7, and it's colorless. But when the single replacement reaction takes place, you're going to form iron 2 chloride. And these iron 2 ions are going to have a really distinct color, like rust. And you're going to form hydrogen gas. So since this first substance is solid iron, if this is taking place in an open container, you're going to lose mass because you're producing a gas. So you can measure the change in the mass of the solid that's being consumed over time. You can also measure the volume change. You're going to obtain a volume of gas. You could also measure the pressure change. You could also measure the color change by using a spectrophotometer. You could also use a pH meter by measuring the difference in pH as you consume the hydrochloric acid. So there are a number of different options that you could look at. If you're down here, you've got a titration that you could do to get the measurement of the concentration change of HCl over time, the pH change using the pH meter from when you're consuming the acid, the volume of hydrogen gas produced using a eudiometer, the pressure of hydrogen gas produced using a manometer, and then if this takes place in an open system, you will lose mass because you're going to produce hydrogen gas, and you can get the mass change. Since I mentioned up above that iron 2 has a distinct color, you may want to write down some other ions, some other transition metals that have distinct colors. Ni plus 2 is a light green, Cu plus 2 is blue, Fe plus 2 is a yellowish color they set up above, Fe plus 3 is kind of a light orangey color. And then Mn plus 2 is a light violet color. Okay, so make note that if you see a transition metal, it's probably going to have a distinct color that you could measure with a spectrophotometer if it's dissolved in water. If you go to the next page and take a look at the practice problems, they want you to indicate 2 methods for determining the rate of the following reactions. Now, there are various answers that you could have here, but if you take a look at the first one, you've got copper solid reactant, silver solid reactant, and then when you form these Cu plus 2 ions in solution, the color is blue. So you could use a spectrophotometer to determine the change in concentration as you're producing those blue ions. You could also do a change in mass. You're losing the mass of copper, you're producing a mass of silver. For B, you're producing 2 gases from 1, so there's going to be a pressure change, and there will also be a volume change. For C, you've got a solid reactant. You're producing a gaseous product, so there will be a volume change again and a pressure change. You've also maybe got a mass loss here if this is in an open container because this carbon dioxide will leave. For D, you've got sulfuric acid with barium hydroxide. You're producing a solid product and liquid water. There should be a pH change. You could also use a conductivity probe because you've got an acid and a base that are being consumed, and you're not producing anything that has freely moving ions in it on the product side. You can also measure the mass of barium sulfate that's formed over time. Okay. Number 2, why would volume of water not be an acceptable answer for 1D above? Well, you don't know if all of this is going to react. You could have some of it still dissolved in the water, so you can't properly measure the volume of water. For number 3, why would concentration of copper metal not be an acceptable answer for 1A above? This is not dissolved in water. It has to be dissolved in water for you to get a concentration, okay?